you confirm whether you can hear my voice or not. Now, okay, perfect. Thank you. Sorry for that. I'll have to go through the slide again. No worries. Okay, thank you. So I will, sorry for that. I'll have to repeat maybe the last 5 minutes. Okay, good. So what is container? As I was just saying that containers is nothing but another way of virtualization. If you want to compare it to a virtual machine, yes, you can compare it to a virtual machine, but unlike virtual machines, container, they don't need guest operating system to run, while a virtual machine requires guest operating system to run. The containers, they share the host kernel. So because there is no operating system layer, they all share the host kernel. And this is why containers run as just processes. So if you look at containers, when they run as OS processes. So containers also, they don't need static configuration. So to run a container, you don't need to upfront say my container will block, let's say, 2 CPUs of my hardware, or 10 GB of memory, or 20 GB of storage. Rather than that, it follows what's called parastable computing. So the container will start and then it will acquire the resources as needed. Definitely, you can control how much resources can be consumed by a container. So this is from system administration perspective. If you're coming from, let's say, virtualization background and you want to compare containers to virtual machines. But from application development perspective, right, we look at containers from different perspective. We look at containers as an opportunity to package your application along with all dependencies. If you're writing Java application and you need, let's say, your Java runtime along with some dependencies, some drivers, some whatever. Yes, this is the way container can help you to package this application along with the full technology stack required for this application to run. And guess what? This application, along with the dependencies, are packaged inside what is called container image, which is portable enough where you can distribute it and get it to run everywhere. So looking at virtual machine, yet you need to have a hypervisor, and each virtual machine needs a guest operating system to run. Compared to containers, no, containers, they don't need guest operating systems. Containers provide the same level of isolation. Containers run as processes on top of the host operating system. And also those containers, also they don't need static configuration, or they don't need the resources to be allocated for them up front. As simple as that. Cool. There are certain characteristics for containers, and we need to remember them. Always remember those characteristics, because this what will get us to deal with the container and to manage the full life cycle of a container. So you need to understand that containers are immutable. So once you run a container, this container becomes read-only. Yet you can log into a container, patch it, but whatever changes you apply to the container, those changes will not be persisted, right? The moment you kill this container, stop this container, everything is gone. And when you start a new container, you start this container from the fresh image. Unlike virtual machine, when you can batch the virtual machine, apply some updates, and this will lead us to some nice concepts when it comes to the container lifecycle management of how do we batch a container. There is nothing called batching container, but there is something called build a new container image, where all the changes are applied to this container image, and then we start a container from the fresh image. You also need to understand that containers are ephemeral. Ephemeral means, right, if the container for any reason writes data to its file system, this data is ephemeral. If you stop the container, the data will go away along with the container. So by default, any data written by the container inside the container file system will not be permanently persisted to your file system. And accordingly, if you stop the container, imagine this is the database container writing to some data files, and then you stop this container, all of a sudden you lose all your data files. And then when you start the container again, it starts with fresh data. Yes, there is a solution how to provide persistence storage for the container, but by definition, one of the characteristics of the container that they are ephemeral. Also, containers, they have what is so-called layered file system. So how the containers store data inside their container images, or how the container image file system is designed, right? It is designed to be layered file system. So you have layer after layer after layer. Imagine you have, let's say, the Java runtime, and on top of it, you have, let's say, a Tomcat server, and then you have your Java WAR file to be deployed on top of it. So just think of this as just 3 layers. First layer where we have the Java runtime, second layer where you have the Tomcat, the third layer where you have your application artifacts. But you need to understand that the way those layers are working, it's actually those layers themselves are immutable. So if you write a layer, you cannot come back to a layer and change it. If you need to change it, you need to write another layer on top of it to either delete files from the layer or add files or even update files. And this is what's so-called the copy on write. So looking at this picture to the right, simply you have 2 layers. Let's assume you're building a file system where you have 2 folders, one called upper and lower. And you can see in the, again, you have the code.python, script Python, and you have code Python, and you have the config YAML, right? And you can see the content of the code Python in both folders. If I build this, let's say, 2 folders in one file system, okay, and merging them using an overlay, which is pretty much what the container file system does when you create those layers. And our expectation is that which code Python will be committed to the new file system. You need to understand the one at the top layer, Even if you want to delete the code Python, it's nothing but you create a new layer where you say delete the code.python. And this is how it works. Every single change, either by adding a new content, modifying existing content, or deleting existing content, need to be committed in a different layer inside the container image. I hope this is clear. So always remember, containers are immutable, ephemeral, and they have what's called layer file system to build their container images. They are also portable, they are lightweight, they are self-contained. So to run a container, the assumption is the container would run independently, right? You don't need to have any external dependency for the container to run. If it's a database, it means the database engine is there, right, with everything required to run the database. If it's an application, it means the application is there with everything required to run the application inside this container. Cool. So how do we run a container then, right? So we have an operating system. We said that containers, they run directly on the operating system and they share the kernel. How do we run it? Do we run it manual? I mean, I don't know how to deal with operating system kernel to say start a process and here is the container image. No, rather than that, we have what's called container runtime. So there are so many container runtimes, and those container runtimes, they do nothing but interacting with the operating system kernel. So for you to start a process, because we said containers are nothing but processes, for you to start a process, you just talk to the container runtime and say that, Mr. Container Runtime, I have a container image having my application along with all the dependencies. I want you to start this container on the current host kernel. And this is the main functionality of the container runtime. It talks directly to your operating system kernel, and it will be able to start the process required to host your container. As simple as that. So the execution flow is that you, as an end user, or maybe your application through some API interfaces, you talk to the container runtime, which one of the most commonly used container runtime is run C. And this is almost everywhere. Most of the vendors and most of the also community projects are relying on the run C. You just tell Mr. Run C that I have this file, could be the container image, tar file, whatever, right? And I need to start a container with this name, sometimes also with this mount, if you need to mount some file system points, or for example, to map some ports, for example, open some ports for the communication with the container, and that's it. So the main objective of having a container runtime is to be able to talk to the operating system kernel to start the process required for this container. There are other container runtimes, by the way, in the market and also in the community, like for example, crun, like containerd, LXC, one of the, I think the oldest one ever, right? But as we said, the most commonly used one, the one you will come across a lot, is runc. Good. So as we said, to start a container, you need a container image. So the container image is nothing but a software package, by the way. When you, for example, package your .NET assembly, or you package your let's say WAR file in Java, right? You end up having all your files packaged inside one software package. So this is very similar, but as we said, it's different in the structure. So container images are nothing but software package where you keep all the container files inside one package. As we said, they are layers. So layer after layer, you have the lower layers, the upper layers, and as we also said, the upper layers always override the lower layers. So if you need to add files, modify files, or delete files, you need to add extra layer to do the same. Also, you need to understand that container images can be built on top of each other. So I can have what is called base image. So I don't need to every time start from blank or scratch image from scratch. No, I can choose one base image, like what we do in programming inheritance. For example, you inherit from parent class. So this is something similar. You just create a container image from a base image, and there you can add your files, right? Keep adding extra files or install extra packages on top of the base image, or even remove, if you want to remove some of the packages inside the base images. So again, container images are software packages, and as we said, they are into layers, and those layers, the presidency always from the top to the lower layers, and containers can be inherited from each other by using base image. So that's good. So now we know what is container, what's container image, what's container runtime. Are we dealing directly with the runtime? The answer is no. Because if you think of it, I need to look after the container lifecycle to say that I need to start a container, stop a container, maybe suspend a container, maybe copy the container image from somewhere. I don't know, maybe some registries or somewhere we have container images, right? And I need to push this image to store it somewhere, like what we do in our software lifecycle management, where we conclude the build and we need to push our build artifacts, something like this. So we have something called the container engine. The container engine is another piece of software, looks after the container lifecycle. This container engine will allow you to start a container, stop a container, inspect an existing container, log into an existing container, watch the container logs, for example, if required, right? And also build new container, right? If you have your, let's say, files and need to package them into one container image, and then pull containers from remote registries and also push containers to remote registries, and they do a lot other than just the lifecycle management. But for now, let's focus on this. But also they can look after, let's say, container isolation, provide level of isolation at the OS level to say that each and every container runs within its own namespace. So containers cannot talk to each other unless we allow so, right? So also they provide storage management for those containers, because we said containers are ephemeral. So if you need persistent storage for the containers to permanently write data to a file system, so the container engine can do this. So in the market, there are so many container engines, but again, the most commonly used ones are Podman, Docker, and Cryo, right? So there are differences between each and every one, but yeah, just to remember that the most commonly used right now on the desktops and for developers is Podman, and Docker as well. You see Docker a lot. Podman is much more lighter, right? And also does not require the daemon to run all the time. And Cryo is the default container runtime for OpenShift, right? So, and all of them are, again, writing according to the Open Container Initiative or the Container Runtime Interface specification. So means if you build a container image, you can run it on Podman, on Cryo, on Docker without changing anything. Cool. So what else do we need to be able to run a container? We need a registry. We said that where do we store our container images? You cannot run a container without having a container image. So there has to be a place where we can securely store those container images, and we can pull, we call them, rather than copy, we can pull those images to our local machines to run a container. Because guess what? You cannot run a container unless you have the container image locally on your system. So if you run it on your desktop, it means I have to have the container image on my desktop to be able to run this container. So container registries are nothing but, by the way, a content server, right, where you store files, but those files are stored in a specific format, and also providing an API interface for someone to call the container registry, let's say searching for images, or pulling an image, or pushing an image, or inspecting image content. So also you need to always remember that you have a local registry whenever you have a container engine running on your desktop, right, or on your machine, right? When you say run, you have a local copy of the container image on your system, right? So how do we define an image inside a container registry? There is always a repository. Under the repository, you will find the container image name, and then you have something called tag. Tag, you can call it a label, for example. So every image to be committed to a repository, you need to assign this image a tag, a label. If you want to compare it to your application lifecycle management, let's call it a version, right? Version 1.2, version 3, version latest, right? If you choose not to provide tag, it will be always tagged with tag called latest. So this is the latest image, right? So for us to look at the registry, we always look at repository inside the registry, and then the list of images inside this registry along with the tags. There are so many container registries available in the market, again, community as well as distribution. Quay is one of them, Harper is one of them, also Nix is one of them, and G4 Artifactory. Those are the most commonly used container registries. So, well, how do we, what is called lifecycle management of a container? For a virtual machine, for example, we understand the virtual machine lifecycle is how to start a virtual machine, then how do you batch an existing virtual machine, maybe how to back up a virtual machine or take a snapshot, maybe how to restore a virtual machine, right, in case it crashes, for example, right, or maybe how to decommission or kill the virtual machine. While in the container case, it's a completely different story, right? As we said, there is nothing called batch an existing container. So it's always, you have a container, this container image has to be available on your local system. If not, it means you need to pull it from the remote registry. Once the container image is available inside your local storage, you can say run a container, and this is where the container will be running, right? And at any point of time, you can stop the container if not required. You can pause it or unpause the container, right? And also you can start an existing container in stop state, right? We call it exit state. So I can start a container running for a while, and then I can stop this container, and after some time start it again, right? So I have stop and I have start as well, right? At any point of time for running container, you can execute commands inside this container. Imagine you have a container, I need to execute some commands inside this container. Yes, you can, right? And then if you stop the container, you can choose to permanently delete the container. By the way, when you say stop, it's not permanently deleted. The container is still there, but the state is called the exit state or stopped, right? But if you want to clear it completely, clean it, or clean your system from those stopped container, you can say delete the container, right? The same also if you have the container image and you don't need this container image anymore, you can say I need to remove the container image, which is called the RMI. So this is the life cycle of a container. Let's start with running a container. So I think the time now to do some hands-on. So when we say container engine, through our demo, we will rely on Bodman. Okay, so you can do the same with Docker, by the way, right? So same commands, same arguments, same parameters. So I don't see any differences if you switch to Docker and try to do what we will be doing here. but we will be using Podman. So Podman, you having the command called run, and to run a container, you need just to have the container image, right? When we say run, first of all, the container will run, and as we said, every running container is nothing but an operating system process. So you can also ask your Podman to show the processes by saying Podman PS. So I can say Podman PS, it will show you all the running containers. If the container is not in a running state, exit state, for example, you can always use Podman BS -A, show me all containers. Okay, so Podman can definitely control the life cycle of a container by creating a container, running a container, stopping a container, and then container also can be reported as dead. Dead means container crashed for some internal reasons, failure or some whatever crashes inside the container. Every running container has something called container ID. And when we deal with the container, so we have an image. Once we start a container from an image, then we have a container ID. To deal with this container, you have to always refer to the container ID. Later, we'll see that we also can give it a friendly name, and we can refer to the container using the container name, right? But for now, let's assume that we have to know what is the container ID, okay? So sometimes, by the way, you need to create a container, but not in a running state. So this is as if you say, Podman, get my container ready, but don't start it. In this case, we don't say Podman run, we say Podman create. And if you look at the state or the status of the container at this point of time, it will be reported as created, okay? So I can say Podman create a new container, but don't start it for now. I'll start it later. And once you create it, the status will be reported created. If you want to start it, I can use the command start by saying Podman start, and you can see now we using the container ID. Okay, so when we started, the container was assigned an ID, and when we created, sorry, and then when we started, we refer to the container ID, and then you can see that the container is up and running, right? It is running for now. If I want to stop the container, I can simply say Podman stop, then provide the container ID. And in this case, if I look at the processes, Podman processes, I can see that the container status is exited. So now we know that I can start a container by saying Podman run. I can create a container by saying Podman create. At any point of time, if I need to query Podman about the existing container, I can always say Podman PS processes. If you want to see all the containers, whether the running ones or the stopped ones, you can always say -A or -A, right? And if you have a created container, you can start it anytime by saying Podman start. If you want to stop it, Podman stop. And then you can always list all the running containers by saying Podman container list. We will switch to a quick demo. I have my Podman running here. I hope the font is good enough to see the screen. So as we agreed, right, everything's shared over the GitHub repository. You'll find the 7 labs, and you'll find the scripts that we will be using during the live session. So let's look at each and every script before we run it. So as you can see, the first one is nothing but a Java application. I just developed small Java application, hello world, right? So for those are writing Java, just hello, printing out hello world, right? And then I compile this application, right? And I can just run it, right? So I can run this Java application, and you can see it's saying hello. If I need to provide a parameter, I just expect it to pass parameter. So hello world, right? So it's a Java application, reads one environment parameter called, let's see the name of the environment parameter, called hello scope, right? And then just printing hello world. So I need to build this container image without getting into the details, but I can say Podman build my container image from the existing. We will get to understand the full build process and how does it work. But for now, I just need to build my container image. So what it does, first of all, it will pull an image from the remote registry, and you can see now the registry we are accessing, and we're using something called the UBI OpenJDK 17 base image. So this is the base image I'm currently using, and if you want to look at how does it look like while we're building the image, we just from a registry we're pulling a base image, okay, and then we copy what? We copy the class file that we compiled, and then we use a command which is Java hello world. That's it. Please run this one. So if I want to look at the container images, podman image list, okay, and now you can see our hello world, hello image, okay, this one. So now instead of running a Java application, I want to run my image, which is running the container. You remember we said simply to run a container, you just need to say podman run, and forget about the -e parameter for now, but as you expect, this is the parameter because the container, my container is expecting an environment parameter called hello scope. So I'm passing this parameter now. So if I go to step number 3 and say this time hello country, not world. So what happened now? There is a container started, and inside this container is my small Java application, and the small Java application was packaged inside on top of a base image, which is the OpenJDK 17, and there is a command inside the container image that says that whenever a container starts, please start the Java hello world, and then the outcome is hello country, right? And in this case, if I say podman ps, guess what? Forget about the running process now, which I can kill it. Stop it for now. So the question is, when we say BS, why we don't see our hello world, right? Because it is actually in exited state. If I say -a, you can see that our my app image, right, which is seconds ago, it's in exited state. And what does this mean? It means the container started, okay, and the process was concluded, and the container finished, and what is so-called exited, right? So this is very important. And if you remember, we also said that the container image is nothing but a set of layers. So let's check how does it look like our application image, the one we just build using our build script. So if I look into this, there is a nice command called tree, and this command will examine the container layers and bring them out. So wow, let's look at this. You can see our image is nothing but one layer of 94 MB, right? Another layer of, which is the base image, 250, and then one small layer, which is this one, which is the 5K. We will get to understand more when we go back to the build topic. How do we build an image, and how do we even inspect what is inside this container layer, each and every container layer. We will see what is inside each and every layer, but for now we believe, yes, we can see it, that our application image, the one we built using the OpenJDK 17 base image, is nothing but 3 layers, and you can see the size of each and every layer. So now that's good. So we understand how did we run a container image, and after running, what will be the status of the container after running. And this is the ID, by the way, of the container. I can anytime say start this container if required, right? And also I can see the container layers. Let's go back to our flow. So this is what we did. We just built a container, and we started this container, and then we were able to see the container details. You can do the same, by the way. You don't have to run any, let's say, images from scratch. You can pull, let's say, a minimum image, which is called the UBI, Unified Base Image, right, for coming from Red Hat, and this is a minimal, very small image, and you can just let's say fire a command, let's say echo hello world, right? And this is the first lab you will be doing, that you just pull one image and run this container, right, with this image, and let's say echo hello world. By the way, when we say run, if the container image is not available in your local system, the first thing you will see is that the Podman will first start pulling the image. So as we said, the image has to be first available on your local system to run. So even when you say run, and this is the first time to run this image, the first task Podman will does is pulling the image to your local system. Once it's available, then run the image. And as we said, you can at any point of time say Podman PS, it shows every thing running inside, sorry, it shows all the running containers. And if -a or -a, it shows even the exited ones. And we have seen when you say Podman image list, it shows all the images available on your local storage. Sometimes after you're done, so Podman PS -a, I can see that those containers are there in exit state, and I don't need them anymore. I can simply say Podman container pro. As you can see, a warning message that by doing this, we will permanently remove all the containers from the system. Yes, but by the way, only the exited containers. If you have a running container in running state, it won't be deleted. So if I say now Podman PS, you can see now that there are no containers available anymore. So going back here, so this is the first lab. What we will do, I can give up to 5 minutes, not more. I wish we can do even in less time, but I know that some of you, if you try, will need some time to pull the images for the first time. But we will go through it, at least run, let's say, lab 1, lab 2, and the rest maybe you can try them offline. So if I switch to my machine, so this is the time. If you want to try, please, first you need to clone your clone the GitHub repository, right, that was shared up before, and then you can see the first lab. We'll just run a container, then we will list all the processes, okay, and then we start the container again once we know the container ID, because when we list the processes, right, or the containers, we'll get the container ID, and then prune all the containers, remove all the containers as long as they are not in running state, and then list all the images, and maybe also we learn how to delete an image if we don't need it anymore. So run a container, as you can see, nothing but Podman run, and we give the image name, which is a full name, including the registry, including the repository, the image name along with the tag, and then we have a command called echo hello world. So if I start with this one, you can see it's nothing but hello world, right? And if I list all the processes, okay, so you can see that there is a process, this one, the one we just run a couple of seconds ago, and it's in exit state, and this is the ID. If I copy the ID and I say now I want you to start this, let's look at how does it look like. The start is nothing but Podman start, and then the container ID, which is the parameter I'm passing here. So as if I say just Podman start this container with the container ID. So yes, container started, right? So, and I can still list 02. As you can see, there is no new container created. It is the same container was again in run state again, and then exited. So I don't need this container anymore. I can say 04 from the container. Yes, yes. And if you want to see the images again, so to, sorry, the running container, you can see there is no containers listed anymore because we deleted them all. And at any point of time, I can see the images by saying that Bodman image list, right, or Bodman image ls, right, if you want. And you can see now this is the image we just run a couple of seconds ago. We said that we need to run this UBI minimal, and there we also said please execute this command hello world. So now we are able to run our first container. I will give it one more minute if you are trying. Okay, good. So that's good. At least now we know that how to run a container, how to list all the existing containers in my system, and internally when we run, how does it work by pulling images from remote registries, and then we can prune or remove all the exit containers if not required, and at any point of time we can also list the images inside our local storage. How do we build a container? This is a very basic question. Why didn't we start with this? So first we wanted to see containers running. How do they run, and how do we, let's say, monitor those containers while they are running or in exit state? Now, how do we build it? There are many ways of building containers. One easy but dirty way, and we never recommend it and never ever go for this, but it gives us an idea about what does it mean building a container image, is what is called commit. Wow. What is commit? Commit means I can run a container image and I can apply changes. That's crazy. So like, for example, what we did with our hello world by saying that every container image of type UBI minimal, I want always, when we started, to echo hello world. This is a small change. Right? It's small, but it's a change. When I say every time we run this container, I want you to echo the hello world, right, message. So one way of committing this container behavior or storing it permanently is to use the command commit by saying Bodman commit. So Bodman, go to the container with this container name, which is the hello world, and whatever changes have been applied to this container image within the container, please commit it as a new image. So all of a sudden it becomes a new image in our local storage. And the next time when you want to run it, I don't need any more to say Bodman run the UBI minimal echo hello. No, I just need to run the new image was created out of this container, right? So this is the commit process. And in this case, after the commit, if I look at the local images, all of a sudden you will see that there is a new image created out of the container, and this image we will see how to run it. So this is the second lab. So we'll quickly switch to the second lab. So if you look at the second lab, we just run a container, and this is for the first time we start seeing this. We can give the container a name, and instead of referring to a container by a container ID, I can refer to the container using the container name. So here, as you can see, just Bodman run, and we're giving the full image name and the same echo world, right? So let's run this one. You can see hello world, and if you see Bodman bs-a, right, you can see, and the name is hello world, right? And if I list the images, so these are the available images. And what is commit now? So commit is nothing but committing hello world. Hello world is the container name. It can be, by the way, container ID if you choose to use the container ID, but we from now onwards, we will always give a container a name, and we will refer to this container by its name. It's a user-friendly name rather than just getting the ID every time. So here we're just saying that, Mr. Bodman, I want you to commit all the changes inside this container into a new image called hello image. Okay, so let's do this. Cool. So if I say now list images, I can see this one 5 seconds ago. So there is an image called hello image, right? It's a new image. And what is inside this image, I can tell you, it is nothing but the UBI minimal along with the echo hello world. And here, if you say run the commit, so I need just to say, by the way, I want you to run this newly created image. And you can see hello world, right? I did not mention any hello world. I did not say any hello world, but you know that the echo hello world is coming from the container, right? That we committed into the hello image. I hope it's clear now, the commit, but this is just to understand what is commit and how does it work. We will never use commit to build container images. There is a better and clean way on how to create and build container images. I will give it 1 more minute for those are trying the lab. Okay, so build. How do we build a container image? So there is always something called a Docker file. Okay, no matter what is the container engine you are using, Docker, Cryo, or Docker, or Bodman, right? So there is always one build file called a Docker file, right? And this is your build script. And this build file, or the Docker file, now let's call it Docker file, has all the instructions required for the container engine to build the container image. So the first thing, as we discussed before, is from, right, which is the base image. You always start with a base image. I'm building my container image based on a base image. So the word from followed by the image name, right, full image name definitely. This what defines the base image. Okay, good. And then there is one common or commonly used command called copy, and the copy is nothing but really a copy from your local file system into the image file system. Again, copy from, you prepare all your files inside your file system, and you say copy from my local path into the container file system, again to the path you want to commit your changes to, right? So it can be any path inside the container file system. Okay, add, it's actually works like copy, but add it has more features. So you can add files from URIs, right? And also those files can be tars and can be extracted directly, right? So yeah, usually we use copy unless you add some remote files over URLs, or also having tar files need to be extracted. Run is just to run commands inside your container. So after pulling the base image and after copying some files, I want to, let's say, add some, install some libraries. It could be, let's say, your yum install or DNS, whatever install, right? So yes, you can always use the run command to run some commands and commit the outcome of those commands to the container image, right? So you say that the outcome of this could be downloading images, downloading files, packages, or whatever, and then store them inside the container image file system. Last one for now is the command cmd. This is where you execute commands. Like for example, in our case, when we decided to run our Java application inside the container image, we just, as we do in our desktop, Java, the class name, in this way, hello world, right? So exactly the same, cmd, Java, and then the arguments, which is the class name hello world. And once you are done, you need to have this Docker file by default, right, within the folder where you have, right, where you run the build. So if I have a folder, and this folder has a Docker file, and from this folder I say Bodman build, and then we give the image name. -t is the image name. -t refers to the tag. So we usually give the image name. As we said, if you don't provide the tag, it will be always assigned to latest, but you can also provide the tag. You can say Bodman build -t my image colon, tag provided after colon, then latest. And dot refers to the current folder. It means go ahead and build my container image, right? So this is how it works. So as we said, the Docker file is nothing but set of instructions, and we have seen how we, for example, build a Docker file from image from base image UBI, then maybe installed HTTPD. Imagine we just starting with small Linux image, and then we adding the HTTP server by just running command micro dnf install HTTPD. And then, by the way, we clean everything after the installation. This is all the Linux administrators, they are aware of this. They know how to install HTTPD package, for example, and then how to clean all the dependencies, because they are not required anymore once you have the HTTPD. And maybe also remove the caching, right, out of the build or the installation process. And then a command is to run our HTTPD server in the foreground. So I want to build, imagine this is an image, to build my HTTP server, starting with plain, let's say, rel image, which is a UBI minimal, and then I added my HTTPD package, and then clean the cache, and then run my HTTPD. As simple as that, right? So Docker file, set of instructions, base image, run, and cmd. In this case, we did not copy any new files. Compare it to the one to the right. All of a sudden, instead of running commands one by one, we started to use the Linux AND operator. So why this AND operator? And what is the impact of having the three commands run into one line, and why it is sometimes very useful to combine commands together? This is what we will discuss together when we do this together, right? But you need to understand each and every line in this Docker file will end up producing an image layer, okay? And we'll see the content of the layer. While if you combine some of those commands together in one line using the AND operator, you end up having all the commands and the content out of running those commands inside one layer. And this can save you a lot of image size or image layers. So unnecessarily creating image. If you look at, compare the outcome of both Docker files, which is, by the way, exactly the same final result, which is our HTTPD server installed and running, right? If you look at the one to the left, you can see how many layers have been created, because each line produces a layer, versus this one, you can see it's only two layers. One layer where we executed everything, right? And then you just have the base layer. So the base image, and one layer when we execute everything, compared to the base image and then 1, 2, 3 other layers for each and every command. So sometimes it's really wise how to build your Docker file and how to build your container images. So to see the container image layers, you have the command tree. You can say Bodman image tree, okay? And then give the image name, and then you can see all the image details. But you can also use a very nice tool called div. Div is much more superior than tree, because div can also give you the list of files inside each and every layer. Not only that, it can also show you what has been added or modified or deleted within each and every layer. Because we said you can build a layer of 10 files, and then to delete one file, inside this layer, you cannot. You just create another layer on top of it to say that delete one file from the layer below. And you also need to understand, if you change one top layer, it means all the layers above need to be rebuilt. So you have to also wisely, right, deal with the layers and how to create them. Before we jump to the hands-on, right, how small it can be, a container image. What do you think, right? Can we build a container image, or let's say like a virtual machine? There is nothing called a virtual machine in megabytes, right? No, the answer here is that you can strip down your container image to be really, really small if you want to, right? If you don't need any other tools, any operating system libraries, any debugging tools, right? You can always start, and there is something called from scratch. Scratch means I don't need anything. I don't need a base image. I'm starting from scratch. And then you can simply copy your files. That could be just binaries. In this case, we're building a small Go application that again prints hello world, nothing but hello world, right? And then we compile it. So Go compiles into binaries, and then we copy this hello world into scratch, from scratch image. And guess what? We build it because this is a Docker file. We say, you know, bodman build -t, this is my hello Go latest, okay? And you can see the size of the image, and it's a running image. It's 1.8 MB, and I can say, find me the layers of the images. So this image, tree, hello Go, you can see it's only one layer that contains my compiled code, my binaries, which is the hello binary, right? And it's nothing but 1.85 MB, right? This is the only content inside the container image, and it is, again, working image. I can say bodman run my hello Go, right? And it runs. Let's do it together. What I want to do quickly, it would take me maybe 2 minutes to start with a fresh view of my bodman. I will remove my machine and start it again. You don't need to do this step. It's just for me to show you how things are working. We didn't start yet the lab, but this is just to show you how do we create those images, how do we build container images out of Docker files, and more important, how do we navigate through the container image layers. Just give me 1 minute for my bodman to start the machine. Cool. So this is the example we were talking about. I have a small Go program. Even here I just made it a bit complex by printing. I'm just trying to add more to become CPU intense, to consume some CPUs, but it's nothing, just a small Go program. And I compile this program, so I have the binary, right, of this. And as you can see, building an image is nothing but build image called hello, latest hello Go, and this is the Docker file. Very simple Docker file. It is from scratch. I don't need any base images, and I just add, right, instead of copy, just I add the file hello from the current folder and command run hello, as simple as that, right? So let's see this image, how small it is, right? And how also CPU intense it is, and how many containers, by the way, we can run and start inside this small virtual machine where I run all my containers. We also have a lab, right? Just wait for the VM to start. This lab is designed also to walk you through the build process. So maybe until the virtual machine starts? This is a question, and I would love to see your answers on the chat. Okay, if you look at this Docker file, okay, which is nothing but building from a base image called node, okay, and assigning a work directory, which is the app folder, then copy all the files of my existing folder to this container image file system. And then for those Node.js developers, they know what does it mean npm install. It means look at your package JSON file and download all the application dependencies, all the npm dependencies, and then build, right? Run again the npm build, right? So run the build process. So if you compare this Docker file to the Docker file below, and the only change you can see is that we just move the copy command between the npm install and the npm build. And before that, we copied before we copy the source code, we just copied one file, which is the JSON file along with the yarn block. And this is where the dependencies are there. If you just quickly on the chat, if you believe, or based on what we discussed, is it 6 layers or 5 layers is better? Now the question, is it only about the number of layers inside the container image or something more? So if you think that Docker file 1 is better, please just in the chat key in 1. For those who believe 2, please key in 2, right? And I'm just waiting for you because we will need to discuss it a little bit. And I'll go back to my virtual machine. Hopefully now it started, and then we can continue the lab. But for now, I'm just waiting for those are voting for 1 or voting for 2. Yeah, so my machine started now. Okay, so let's go to our script, minimal. And as we said, you can see there is a small Go program, right? And this small Go program is nothing but printing some data, right? And I need to build the image. So if I say Bodman image list, that's good. There is no images. This is why I started a fresh VM with no images already loaded. So let's first build this image using the Docker build. That's it. It's from scratch. This is why we did not need to pull any base images, because it's from scratch. And if I query the images now, I can see that my hello Go, which is latest, by the way, because if you look at the build script, I'm saying yes, please build, and this is the tag name, hello Go, and give it the tag latest and build from the current folder. And we all have seen the Docker file, which is from scratch. Copy the hello, add the hello file, and then run it. So it's nothing but 2.02 MB, right? So because I just added more scripts. So let's see, for example, how many containers I can run. I can run a lot of actually containers on a small VM that actually nothing but one vCPU, right? If I say here, if you look at this, I'm just running 10 containers for now. So, and this is the hello Go, right? So I can say, for example, Bodman run hello Go. You can see this is one hello Go. What it does, it's actually looping, right? And every 20 seconds, it's just printing random number, take from, right? So, and I can stop it, right? And accordingly, if I say Bodman bs minus a, I can see, yes, there was one container running and now it is in exit state, right? And this container coming from the hello Go image, which is nothing but 2 MB, right? So let's run, let's say 10 of those images all together. You can see each container, when it runs, it prints out the container ID and also the IP address of this container. Every container, when it runs, it's assigned an IP address. And if you want to see those containers, for example, yeah, this hello till hello 10. If I click on any of those containers, you can see the logs coming out of the container, right? See, so I can also check container 3, right? So you can see, and if you see those containers and I want to stop those containers, right, I can just say 04 stop, which is nothing by the way but container Bodman container stop, right? So you can see that hello one go stop, right? And you can see them here, right, from running into exit state. So we will just kill the 10 containers we created now. And if I go back, I just also broom, so it means remove all the container images. So if I go to bs-a, there is nothing running because we stopped everything. So this is the build process. So we have a lab, which is lab 3. This is lab 3. Right. You have a Docker file, as you can see. We are building a new image, which is your HTTP server, and this is very interesting lab because you will get also to do what? To yes, here you will get to also build your HTTP server, and you can also push some images if you some content, static content. If you want to push your HTTP files, your images, your style sheets, your JavaScripts, you can also push them inside the container image and start using it. So first let's build the image 01, right? Build the image. So as you can see, for the first time, because we started fresh, we're pulling the UBI minimal, right? And once it is pulled from the remote registry, and you can see the run micro DNF, which is install HTTPD. So the installation is happening now. So I'm writing now to the container image file system all those dependencies, right, required to install our Apache HTTP server, right? And accordingly, it will require actually some packages to be downloaded. Everything will be downloaded. The reason why I wanted to show you this, because we wanted to see the image layers out of the build process. And the Docker file that is used to build this image is what we can see now. So now this is the installation going on. And if you look at the build image, our HTTP server image name will be my HTTPD, right? So the last step, and then we have the image. If we clear and say Podman image list, you can see my HTTPD. This is the one. This is the one we built, which is, by the way, 168 MB, having the minimal UBI and HTTP server, right? Good. So let's for example see the Bodman image 3. You can see the layers. So we have 1, 2, 3, 4 layers, right? And the first layer is the base image and the other layers. If we look at dive, this is much more interesting because it will show us everything about the layer contents. Very good. You can see the layers. So from the install, and you can see the to the right, even the file, the folder and file structure, right? So if I look at, for example, the RM minus RF, what do you expect from this layer? My expectation is that there is nothing added, there is nothing updated, but it's all about deleting some files. Do you want to make sure? Yes, let's tab, it moves you to the right side, and you can see down there are some filters. I can say Control A, show me the added files, Control U, updated files, and Control D, deleted files, right? So yes, I can see that for this layer, which is the rm minus rf var cache, I can see that it's only one folder was deleted, which is the cache yum look, right? So one complete layer was created for sake of deleting files, not adding file. If I go, for example, to the layer above, you can see, by the way, clean, the micro DNF clean all, you can see how many files have been deleted, right? And yet it's delete, file delete, but we had to create a container image layer for this. So before we leave this one, let's build a better image. If this is the case and we keep building layers after layers, let's build a better image, 02, and we'll just keep it running for sake of time. We'll come back to it once it is done. I think it will just take 1 minute. So this is lab 3. Good. Image tags. Now we understand what is image tags, right? That every image has a tag, which is the label assigned to this image. And by the way, for you to push a new image to any remote registry, you just need to tag it. And in this way, when we tag it with the full name, including the remote registry name. So now maybe my HTTPD image, the custom image I built, right? I want to push it to my registry. So I can say, yes, go to the Quay.io registry and go to the WL2000 repository and then push this image with this name, right? So once you tag it, you can push it. So again, the push is nothing but tagging an image with the right full name, including the registry name, the repository, and the image name and tag, and then you can push the image with the same name, right? If I look into this quickly, yeah, so our image is done, by the way. If you want to compare both, so you can say compare, you can see now the HTTPD, it has those layers. You can see those layers, 4 layers, while my better HTTPD is nothing but 2 layers. And if I want to dive, I can dive, right, inside this image to see how does it look like. I'll leave it to you how to dive inside the HTTP better and to see how did we reduce the number of layers. The question about this, I did not see. Yeah, looks like, okay. So the question about this image or the Docker file is that I can tell you that number 2 is better than number 1. Why? Because you remember we said that whenever you update a layer, all the layers underneath need to be rebuilt as well. Okay, so in this case, imagine every time you copy your source code, you build an image. And you can rebuild the image, by the way. Every time you change your, let's say, Node.js files, I need to package them inside the container image again. With the first Docker file, every time you copy the new files, what you do, you actually resolve dependencies again and you keep downloading them using the npm installer and then you build again. While in fact, I need to resolve dependencies once and only once if I change the package JSON file. That's it. Otherwise, I don't need to reinstall the dependencies again. This is why by moving the copy source code between the install and build will save you a lot of time building this image, because what you will do, you will just copy the package declaration file, package JSON, and run all the dependencies. For the next rebuild, image build, if you change the source code, you just need to build one layer, which is what? The npm build, to build your binaries inside the container image. I hope this is clear, but I just wanted to show that it's not only about the number of layers, sometimes also it's about the logic you put together to build your container images. Ports. If we start a container image, how do we communicate with this container image? The container runtime provides you with the mechanism to map the host port number to the container port number. So imagine the HTTP server we just created now, right? How can I run and start hitting the URL to serve the content from this HTTP server, right? So it's simple. I can say, Mr. Podman, when you run this container, the container is expecting a traffic on port 80. But guess what? I want you to map the host where the container run, port 8080 to port 80. So I can simply say -b, so run this container image, -b docker please, or podman please, whenever you get a request over port 8080, please send this request to my container on port 80. As simple as that. Okay, so again, you can run the container and map the container ports to the host ports using this nice parameter -b. The first one is the host, don't mix please. The first one is the host port. This is where you will open your browser and type localhost and use this port number. And the second one is the container port number. Okay, and always remember that you can run a container in the background by using the -d, right? So -d means if I start my HTTP server, it works, but it will always keep my prompt busy, right? With it, like this. If I want to run it on the background and I forget about it, I always can use the -d, right? So let's quickly do this, lab 4. As you can see, is nothing but running a container image, right? Which is from Docker, run the HTTP server, right? And we just give it my HTTP name, right? So I will switch to lab 01. So putting the image, because again, for the first time, I'm using this image. Oh, my server is up and running, by the way, and responding now. If I go back and say localhost 8080, refresh, it works. If I come and stop the container, shutting down, and then refresh, it's gone, right? So because simply I just choose to run this container on the foreground, not the background. I have the same version of the command, but using the -d. And this means if I run it, it will start, and you can see it will print out the container ID, and the server is up and running. Server is running. You want the proof here? It's responding, right? But I have my prompt back. What if I want to see this? So podman ps. You can see this is a container, and by the way, the name is my HTTPD. I can refer to it using the name. I can also say podman container list. Both commands will give you the same, and I can also say podman stop my HTTPD -d. Stopped, and if I try to refresh, it's gone, right? So this is again quickly how do we map, and you can see the mapping is happening from the -b, right? Saying that please map this port 8080 to the container, because the HTTP server is expecting port 80. So I'm just mapping from port 80 container level to port 8080 host level. Okay, we go quickly for sake of time. Okay, environment variables. So don't you expect your application, your database, your server, your image to again ask for some environment parameters, environment variables? Database, for example, to start the database engine, you need, let's say, username and password. You need maybe the local database, right, to be created right inside the database engine. So this is why the container runtime or the container engine provides a mechanism to pass some parameters to your container images. So when you start the container or run a container, there is a mechanism to pass some environment parameters to your container image using the -e, right? So -e is the environment parameter, and definitely followed by the environment variable name equals the value. If you look at the simple hello Java application we developed, it's actually reading a system environment variable called hello scope. So as you can see, right, when we build this container image, we start running it, my application is always expecting an environment variable called hello scope. Then how do we pass this hello scope? Is nothing but, please, when you run it, provide me with hello scope environment variable, and you just give it a name, hello city, hello country, hello town, hello whatever, and run my image. So what is happening? The container engine will pass this environment variable to the image, and as you can see, for example, the print out will be hello town or hello city in this case, because what is happening, the container image or the container will run the environment variable directly from the run command. So this is again another, or the mechanism of how to pass some variables to the container images. We have a lab for this, please go through it. I will quickly execute it, and we don't have time, you can execute yourself offline. So this is lab 5, and you can see starting a container with some variables. So you can see greet hello and target hello. You can pass, by the way, as many variables as you want, hyphen e, hyphen e, hyphen e, right? You can see now I'm passing 2 variables, greet and target, and it's nothing but our lovely UBI minimal, the one we pulled before. And here I'm just using the command print environment, so just printing the environment variables as we pass them. So 0, 1 hello world, that's it. So because I passed hello world here and I'm passing it here, but isn't it realistic if we talk about database engine? Okay, good. So let's start our database engine, in this case the Postgres database. And we know that to start a Postgres engine you need 4 parameters. One is the username, password, the database name, and the port, right? The port, right, which is the running. So we passing the 3 environment variables, username, password, and database, and also we mapping the port from the container to the host name. So if I start this one, so I will end up having a database engine, and you can see -d, so it will run on the background. So once the container image is pulled to my local registry, I will have a database engine running. This database engine is actually using the username admin, password, and using created a default database called demo, right? And it's waiting for me to connect. And you want the proof? Yes, I can say bootman bs, and you can see, right? You can see the Postgres 12 is running. And guess what? I can connect. If you look at this, exec, it means I want to connect to this container image and execute some commands. Let's say create a table and then select some variables, right? So, select some rows from the table. So I'm just running database connect, and you can see, 03. You can see insert data, right? And if you want to make sure, I can say validate 04, which is select from table. You can see now we just here connected to the same running database container, and using the username admin, password is the default password, and database demo, and then select star from the container table, the one we just created in the previous step. So quickly, we created a container database. We used the -e to pass the environment variables, and then we used the -b to configure the port, and we were able to connect to this container database and execute some DMLs to insert columns and select columns again from the database. And I just need to speed up. So volumes. Containers are ephemeral. So by the way, the container database, the one we run now, because we stopped it, if you start it again, right, guess what? Nothing will be there. Even the table we created, which is create table demo, right, it won't be there. Why? Because it's ephemeral. Once you kill the container, all the data goes away with the container. So if we start a new container, we start from scratch. This is why there is a mechanism with the container runtime to pass or to configure or to mount external volumes, right? So, and for this, you need to use the -v or -- volume, and there you map from your container path, right? For example, a data file, or let's say the www root of your HTTP server into your, let's say, the container image. So from your local system into your container image system, right? File system. So, and this is where you can say, I have a folder where I prepared all my files and I want to mount this file. So now you have access to the file system, yes, because it's your local system, but the container engine will be able to mount this local folder as what? As a volume to the container. And hence every data read or data write will happen against your local file system. And when you switch off the container or stop the container, what happened? The data is permanently stored in your file system. And when you start a new container and you mount the same volume, you end up using the data that was created by the previous container. So this is the idea behind mounting, right, volumes or resistant volume to the running containers. Okay, so you have different mount options. By the way, you can have read write, you can have read only, right, and also you have the read only write and read write, right, options. The point is that when you do something like this, make sure that you use the right mode. Why? Because sometimes maybe you mount a read-only volume, but your container is expecting data to be written, so it will fail. Definitely, you will not be able to write data to this volume because you choose to mount the volume as a read-only volume, even if your local file system still allows read and write. But for this container, because the runtime will strict the access of this container to the file system to be read only, right? And you can see we have an example, right, lab, where you can create your own HTTP server, right, and then you push some new files inside the file system, your local file system. Accordingly, what happened, the HTTP server will be able to serve new content. Okay, we have a lab for this. Please go through it, right, because of the time. So by end of this, at least we understand what is container and how do we build a container image and where do we store containers, either in our local system or remote registries. How do we pull a container image? How do we tag a local image, and how do we push it to a remote registry? How do we create a container? How do we start a container? How do we stop it, right? How do we monitor or list all the existing containers, either the running ones or exited ones, right? How do we map ports inside containers to our host ports to be able to communicate with containers? And how do we pass environment variables to the containers to be used to configure our internal processes running inside the container? And also, how do we provide volumes or mount volumes to those containers? So the second topic of today is a Podman. Podman, we've been using Podman now for almost 1 hour, right? So Podman is, as we said, the most commonly used container engine, and I requested you to download it to your desktops. So Podman is an open source, right? And it's the most preferably kind of developer tools, right? Especially if you're running your Windows, your Linux, your Mac, right? It runs everywhere. Yes, containers are Linux. Nobody can doubt about this, right? Or can debate about this. So are we expecting Podman not to run on Windows or Mac? No, it runs. It runs. And the good thing is that it's using virtualization software to start a virtual machine. So in fact, all what I was doing all the time was against a virtual machine managed by Podman. So it's not running directly on my Mac OS system, right? So there is a machine created and managed by Podman where all my container lifecycle is managed inside this machine, right? And for this, Podman provides a nice command called machine, where you can list all the existing machines. You can create, by the way, as many machines as you want, but you can have one machine running at a time. You can start. So first of all, you need to init the machine. You can also start and stop the machine, and you can remove the machine completely if not required. Like what we did during the demo, I chose to remove one machine and re-instantiate this machine again to start fresh, okay? If you don't provide the machine name, Podman always assume that it's the default. So Podman, if you say Podman machine init, it will initialize the default machine name without a name, right? So if you say start, it will always start the default machine name. Otherwise, if you want to give it a name, start a machine with name, please provide the name. So you can say Podman machine init, Podman machine start, Podman machine stop, or remove the machine name. And as we said, either on Mac or on Windows, it relies on the virtual machine software provided by the operating system. In the case of Mac OS, you have the QEMU, and in case of the Windows, you have the virtualized Windows system for Linux, the WSLV2, right? So both are required for you to run Podman on Mac and Windows. If they are not there, you need to, I think Mac by default it's there. Windows sometimes, some systems, some enterprise environments, they strict using WSL v2. So it's anyway required for you to run Podman. And once you have it, you can see the machines. So end of the day, you need to understand, yes, this machine is a Linux. So the Podman machine is nothing but a Linux machine. But if you don't like to deal with Linux, if you don't need to deal with it. Just deal with Podman, do everything through your Podman. But if by any chance you want to, let's say, see what is running behind the scene, you can always say, Mr. Podman, show me your machines. Yeah, you have the machine. I can also say Podman SSH to so right now I'm not on my Mac system, I am on the Podman machine, right? And this machine is, you can see it's core, which is a flavor of Linux, right? But you don't, as we said, we don't need to deal with this. You can always deal with the Podman directly. So also when we say Podman run or Podman, let's say Podman run Nginx. This is funny a little bit because I did not tell Podman where to find Nginx. But at the same time, you can see that Podman immediately started to look for Nginx at the Docker.io registry. So what tells Podman where to find the container images? There is always a configuration bare Podman machine. It's called the unqualified search registries. So if I log into my current machine, I can show you this. So anyway, the Nginx is running now. I will stop it and then Podman inside my machine. So I am inside the Podman machine, which is the Linux machine, and I can show you, I can cat this file. So this is a configuration file inside the Linux machine of Podman, and there you can see the unqualified search registries, and they are in order. Okay, you can see first we'll search for this one. If not, you can search for this one. If not, you can search for this one. The last one is QIA. So when you provide just the image name, then the Podman will always look at the unqualified search registries in order trying to find those images to pull them from the registry. Right? If you want to customize it, definitely you can remove everything and keep your, let's say, corporate internal image registry, or your, let's say, another private registry where you keep your images. This is why if you, for example, I can say Mr. Podman search MariaDB. You can see what happened now. So immediately Podman will go and try to find MariaDB on the different registries, but the first one definitely will be Docker.io as listed in the unqualified image registries. I hope this is clear, and this is really helpful to customize your Podman machine. Also, for any registry, private registry or registry that requires authentication, you need to make sure that you log into this registry. So Podman login -u-b username and password, and they provide the registry name. Okay, good. So also Podman provides network infrastructure, so you can create any number of networks inside Podman. The default one, it's always created by Podman. You don't need to worry about this. It's always there, which is the default bridge network. And every network has a CIDR, right? So the IP range, when you create containers, what happens? The container is assigned an IP address, and the IP address is given from this container network range, IP range, right? So you don't need to worry about this, but you can, any point of time, you can create a new container, new pod network. So if I say Podman network list, you can see it's only one network created now. I can go ahead and say Podman network create and provide the container network name, And you need to understand that when you create this container, it's given a name and also a subnet, right, where you have the CIDR, right, or the range of IP address can be given to your container inside this machine, right, or connected to this network, sorry. So if you choose, for example, to give a range of, let's say, 5 IPs, so you can run only 5 containers at a time connected to this network, because the network will not be able to assign any new IP addresses for this container, right? So the commands are very straightforward, right? You can just create a container network by, say, container a Podman network create. And also when you run the container, if you want to attach this container to the network, you just need to provide -net. You can see here I created network demo or demo network, right? And when I run this container, I want this container to join this network, right? To join this network. And accordingly, the network management of this container will be managed by the demo network, means the IP address assigned to it and everything else provided by the demo network. You can also choose to attach this container to multiple network interfaces or multiple networks. So if I have my Podman, the default network and demo network, I can run this container and say, listen, connect to both demo and Podman default network, okay? And you can, guess what, even if you have a running container, you can choose to connect this container to a Podman network, right? So it's a running container, and you know what, just this container I wanted to connect to my demo network. And this is very interesting if you also need an extra level of isolation. So now we know that by default, every container is isolated within a process managed by the operating system, and the lifecycle management is managed by the engine as well as the runtime. But also for the networking, if you need to make a full separation between different set of containers and other set of containers, you can always manage it through the Podman networks and provide their range of IPs can be assigned to each and every network. Okay, good. So the most interesting part of Podman is what's called pod. Right now we're dealing with containers. So Podman provides a new definition called a pod. A pod becomes a minimum unit for manageability inside Podman. So instead of running a container or stopping a container or starting a container or creating a container, what if we need to deal with many containers together? Let's say 3, 4, 5, 10 containers together. So yes, there is a way Podman can manage them by grouping those containers into what's called a pod. So a pod is a logical grouping of many containers. Yet those containers, they share the same namespace, OS level. They share the same IP address, by the way, you like it or not. So if you run 10 containers within a pod, the pod is assigned an IP address, and those containers, they all use the same IP address of the pod. And it means also that the port space is shared across all the containers. I cannot start 2 containers inside one pod having the same IP, same port, right? Because it will be a port conflict, right? So, but the beauty about pod is that I can manage the whole container set inside the pod at once. I can say start my pod, stop my pod, pause my pod, delete or remove my pod, and accordingly all the container inside the pod will be impacted by the pod lifecycle. So instead of dealing with container level lifecycle, we're dealing with a group of containers from the pod level. So this is the definition of the pod and how Podman is managing those pods. So again, like all other objects managed by Podman, there is a command called pod. You can create, right, and you can give it a name, and you can also assign some labels, helping you later to search for pods or to select some pods, right? Also, you can start a pod, like what we did with containers, and map those pod ports, default ports, to host ports. So imagine now we're starting a pod, and we want all the container inside the pod to run, but only one, maybe one of them, right, that's listening to port 80, to be mapped to the host port 8080. Yes, this is doable. And it means when I start a new container, I don't need to do a port mapping, because the port mapping is already done at the pod level, right? I just start my HTTP server. That's it, okay? And the HTTP server, because it runs within the pod, it knows that there is a port 80 mapped to host port 8080, and accordingly all the traffic will be delivered to this container. Okay, how does it work? It's not a rocket science. It's very simple concept. Every time you create a pod, what is happening? There is a default container running within a pod. You know nothing about it, but it is running. It's called the infra container. So again, every time you start a pod, you create a pod inside your podman, by default there is a very small tiny container running there. It's called the infra container. This infra container has everything about the pod. So the pod itself is just a name, right? It's just a logical name inside podman to manage a set of containers, but the details of the pod are maintained inside this infra container, including the IP address assigned to the pod. So the pod, like all other containers, when you start a pod, it is assigned an IP address. So where do we store this IP address? Inside the infra container. Okay, let's say the resources allocated to this pod. I can say my pod. Now we started to see interesting things. I can say my pod, no matter how many containers running inside, I want to limit the CPU utilization to, let's say, one CPU only. You cannot consume more than this. Yes, this sort of data, either hard or soft limit, are maintained and stored inside the infra containers, right? This is why if you start an empty pod and you query the container inside it, you will always find this infra container, including even the level of isolation, including C groups for the resource allocation, everything, right? And the namespace kernel level where all the containers inside the pod will be running, everything is maintained inside this infra container, right? So the idea now is that when we started, right, we started with an infra container, and this container is coming from just a very small, tiny, small image called pause, right? This is why it is suspended all the time, right? Unless you start dealing with the pod, right, to read the configuration, right? So you can, by the way, override this default image but I don't see any value, right? Unless you really have specific configuration or some extra configuration need to be configured at the pod level. So if you want to start a pod, you just say podman pod start, right? And if you want to inspect this pod, you can inspect it to see how many containers running inside it. And if you want to see the infrastructure container, you can simply JSON query, right? Because inspect, it actually returns JSON formatted string. You can JSON query and find the infrastructure container ID. So in this demo, what we will do, let's together create one pod, and inside this pod we'll run a Postgres database, and then we'll run the Postgres admin the web console, right? And then we connect from this web console to our Postgres database. Let's quickly do it because this will be interesting to see the So as we said, creating a pod is nothing but using the command pod create. You give it a name, and here I'm also mapping a port. So internally, the Postgres admin web tool, it's listening to this port. It's just I'm mapping it to the port 80. I'm mapping it to port 9876. So I will go to app 7, create the pod, and you can see now there is a pod called learn SQL created, right? And if I say podman bs, there is no processes running there at all, right? Except that we have a pod running which is learn SQL, right? If I say podman inspect pod inspect learn SQL, you can see this is the inspection, right? And there, if you look at for the container, infra container ID, you can see this one. So there is an infra container ID running inside this pod, but we don't get to deal with this infra container because it's meant only to manage the pod, right? And inside the pod, you can see the port mapping, for example, right? So all the configuration now are maintained at the pod level, not at the container level. So in this example, what we will do, as you can see, we will run one container image, which is Postgres, and we'll run the Postgres admin, right? So let's run both. So and as you can see, we are using the environment variables. So yes, we're running both in the background, and we give them name, and you can see the pod. We're running both inside the learn SQL pod, right? And for the Postgres admin, you can see that we have a username admin at demo and the password, the common password. So we'll just wait for the image to be pulled and started. Very good. So we have both now running. And by the way, if we still say Bodman piece, now you can see we have two containers running, but we have also third container running, which is the infra container. So only when we started to deal with the pod by running container inside the pod, the infra pod wake up and started to do the needful, which is the, again, creating the pods and assigning everything required for those containers to run inside the pod, right? So let's look at the system, local host. I think it's 8 or 9, 8 and 7, yes. Until it comes. It's very important to see that pods can be seen here, right? If you look at the, we will come to the Bodman desktop, right, to deal with it. I can see that pods are can be seen here, and this is the logs, by the way, including our database log and including the admin log, right? And also you can see the containers, 3 containers running inside the pod, including the infra pod, including the database pod, including the admin pod. Here you can see it's demo for admin at demo, I think. Yeah, admin at demo, and the famous password. Very good. So this is a generic Postgres. Let's register a new server. So server is local, connection, local host. Don't be surprised, because when containers run within a pod, they all share this local host, right? So you all have the same local host. Password is, let's make sure password is password, be capital, password. Save the password, save. You can see we are connected to our database, which is running inside a container running next to this container in the pod, right? And you can see that the command is nothing but running the same container, and we pass the pod name, right, to container to run inside the pod. Quickly, because I think we just have 10 minutes. Very good. So this is the example we have seen, and you also have lab for this, lab 7. Please go through it and make sure that you are able to create pods, and you are able to, again, by the way, you are able to start, stop pods. So if you look at this, for example, podman, pod, learn, stop, learn, SQL. You stop the pod, and if I come here, you can see not only the pod with all the containers inside it already stopped. If you want to start, you can simply start the pod again. So this is the pod level management. As we said, you don't deal anymore with the containers. Everything is done at the pod level. You can start the pod, you can stop the pod, I can remove the pod if required. That means all the containers inside the pod will be removed as well. Very important to understand that all the containers inside the pod are given one and only one IP address, which is the pod IP address. You can see the pod started again. So yeah, the desktop is nothing but a desktop tool given to, again, users to be able to manage your underlying podman. So I don't need to deal with the CLI if I choose to not to. For example, machines. If you look at the settings, so this is the podman desktop. You can see that I have one machine, which is the default machine, and I can create new machines from here directly instead of saying podman machine init, podman machine start, podman machine stop. I can do everything here. I can restart my machine, I can stop my machine, I can delete my machine, I can look at the details of the machine, including resources, right, and the other. I can look into the logs of the machine if required, right? So this is the machine level. There are some plugins for Podman, by the way. Podman can be used to manage your OpenShift local or also Kubernetes if required, right? So, but we'll not get into this for now. At least Podman at the very, uh, I would say, elementary level is that deal only with the containers and bots for now. And if you want to use the desktop, use the desktop to manage your machines. You can create new machines if required. And also you can look after your container. So right now I can see I have so many containers running here. Sorry. And some of them are running within a pod. Others are just running as pure containers. I can start a container from here directly, by the way. And I can, you remember the command podman container prune, which is again prune all the unrunning containers or the container in exit state. I can start, if you want to start this, for example, I can start it, right? Or I can stop the entire pod from here. If you go to pods, this is the pod, right? And you can see pod level, I can stop the pod. It means all the containers inside the pod are stopped. I can start my HTTP server. So it's running. If I go back to localhost and 8080, it works. If I want to stop it, right, I can stop it, right? So it's just saving you the hassle of dealing with the CLI, the terminal, right? Where you can say, start a container, stop a container, pull the container image, right? Or create a new container, right? Where you can sorry, provide the container Docker file and do the, again, the Docker, the container build for me, or use an existing image. And these are the images, by the way. Do you remember? We said that every time we say podman run or podman build, end of the day, you have a local copy of the container image inside your local storage. You can see all the images, either we build, including, let's say, the BG admin, the Nginx, HTTPD, or the ones we build, like HTTP, my HTTPD, my better HTTPD, all are stored here, right? And you can choose to run them directly from your, as if it's just a small local image registry inside your podman. So again, either you manage your containers, you manage your pods, you look at your images, or you have the volumes, which I created one machine mapping, let's see, a local file system or local file directory file directory to the one of the volumes there. Or else at a higher level you can also manage your machines. Because we're running out of time, we have 6 minutes, and I think we are done, except for one small catch for the Java developers. Please look at the JCube. JCube is a set of plugins for Maven, right, and also given for Gradle, right, to help you to deal directly with containers from your inside IDE using the same build tools like Maven or Gradle. If you need to build a container image, you don't need to write Docker files at all. The plugin will do it on behalf of you. So you need just to say, listen, Maven, I have my JCube plugin. JCube plugin internally using something called JIP, which is the Java Image Builder. And this Java Image Builder, it knows how to build a container image even if you don't have Docker and Podman in your machine. Don't worry. So imagine I have a pure Java development desktop. I don't have Podman, I don't have Docker, and I only have the JCube along with JIP installed there, which is the Java Image Builder. And I can say, using Maven, my traditional Maven command, please package and use Kubernetes build. And accordingly, all the required file will be generated and the container image will be created for you without even writing any Docker file. But if you're still curious to understand, you can always say, in this case, for example, if you're building for Kubernetes, you can say Kubernetes resources, and you can always see all the produced objects, including, let's say, the Kubernetes objects required to deploy your image, like a deployment object, a boot definition, service definition, all those can be defined. But the main engine behind it is JIP, right? So this is a Java Image Builder. It's part of the JCube if you install it. And it's a dependency along with the plugin. You need just to define it inside your Gradle or Maven file. And from your Maven file, you can say package, but in this case, I'm not packaging a WAR or FATJAR file or Enterprise Archive. I'm packaging a container image by just saying, you know what, use the Q8S, which is Kubernetes, right, build. And in this case, the outcome of this build will be a container image. And if you want to push it directly to the container registry, and there is also in the plugin configuration, you can configure which remote registry you want to push your images to. You can say, you know what, also don't keep it only local, my local storage, but push it to a remote registry. You can say Kubernetes push, so it means also as we do podman tag and podman push, this is also happening using the jib tool. So it's a very handy tool, and I would strong every Java developer to give it a try, right? We have an example here, shows end-to-end how to use it inside a Spring Boot application, and how do you build the container image, how do you push the container image, and later how do you deploy it directly on either Kubernetes and OpenShift. We'll see it later when we come to Kubernetes and OpenShift. I think we are done. I have 3 minutes. I assume that all the questions have been answered. I can see Rami very active on the chat. Thank you, Rami. And I hope, yeah, I was able to cover as much as I can, but I know that there are some parts still needs further, let's say, study. So give it a try. I will definitely have a link to this recording on my LinkedIn page, and will leave my personal contacts right on LinkedIn. You can reach out to me in case you need any help, any support, or struggle with any of those labs. Thank you for your time, and I hope you enjoyed it. And we will announce the next session, which is the introduction to Kubernetes, and the ones after that, yeah, we'll just finish one by one. So the next milestone will be our introduction to Kubernetes. Okay. Thank you all, and hope to see you again in the next session.